So we're now going to show the simulation of the very simple but complex equation that we've described. So if you've seen in the video the first cause of chaos, which is slight differences in the initial conditions give serious chaotic differences after a number of iterations. Now we're going to simulate with the A value or the mu value. Now this is, for those that haven't seen it, a DOS simulation. It's a little bit old, but it still works, and at least that's a little bit of industrial archaeology. So I'm going to give each time over and again the same starting value, which is 0.1. So in order to avoid the first type of chaos that you've seen on the DVD. I give a mu or an A value of 2, for instance. It asks a number of iterations. That's a technical matter, so I'll give each time the same. And I give first order. First order means that xn plus 1 is function of xn. Second order would be xn plus 2, function of xn. And you see perfectly nothing, since the stepwise approximation perfectly fits the parabol. The line that you see is a diagonal for which the x-axis xn values are equal to the y-axis xn plus 1 value. So if you take 0.2, you go to the diagonal, and you go to the left, you fall on 0.2. Doesn't matter for this situation, it will matter in a minute. So I start over, and each time I'll have to start over. So I'll go rapidly through that, right? So again, I start with a value of 0.1, as I said. I now go to a mu value of 3.4 as an example. I again give the number of iterations that he asks, and I again give the first order. And here you see something very remarkable. For a while it goes smooth, and suddenly it starts jumping between two values each time, from value 1, which is an attractor, to the diagonal, to the second attractor, back to the diagonal, to the first attractor, back to the diagonal. If I would give a number of hundreds of iterations more, it will continue to iterate between these 2 points for an ununderstandable reason. I go further. So I go now, again a return map. I again give 0.1. I increase the value to 3.7. 100 iterations, 200 iterations, first order. And here you get complete chaos. So in the beginning it goes perfectly nice, and then it starts iterating each time over the diagonal, and then it goes back to another point on the parabol. So you see that you have here tens and tens of attractors. So the thing is jumping from one value to another. So there's no smooth behavior, there's no parabol anymore. It just jumps incredibly, right? This is a chaotic situation. So clearly, if mu is, for instance, equal to 3.7, you get chaos. Now, I continue, and as you can imagine, of course, if I raise mu even further, then you will see, so again, 0.1, as I said, 3.9, for instance, 100 iterations, 200 iterations, first order, and you see not necessarily more chaos. You see that the chaos is spread wider over the parabol, right? Now I'm going to show you 2 more things. One, a last simulation, which I do with a particular value. So again, I give 0.1 in order to avoid the first type, and I give now as value 3.84. You'll immediately see why I give that. 100, 200, 1, and you see only 3 attractors, and the thing is now forever going to iterate between those 3. So for the value of 3.84, despite the fact that it is in between 3.7 and 3.9, you suddenly get sort of a calm situation. It's precisely what happens on markets, by the way. Now, I could give you an overview of that, and then I give you the so-called bifurcation diagram. And we look always x equals 0.1, the same iterations, of course, that doesn't change, 200, and I go now to show you all the simulations for a mu going from 2.8 until 4. And what you see here, for instance, is until that on the x-axis the mu is 3, you only have one attractor, which means that as long as mu is smaller than 3, the approximation perfectly fits the parabol. From 3 to 3.4 you have 2 attractors. That's the first simulation I showed you. So it's going to bounce between those 2 values. And then it's period doubling. So it goes from 4, 8, 16 to many, many, many. And if you go now at the right side of the diagram to the value 3.84, you exactly see the 3 points that you've seen in the last simulation. So what this shows is that depending on the value of A or mu in this very simple but complex equation, you can either get a perfect approximation of the parabol by a stepwise function or a completely chaotic approximation. You don't know when it happens, you just know that it happens.